Hello, everyone. This is Liyi from Riken in Japan. I will give a kind of introduction lecture to the idea of so-called spectrum model error or atomic data uncertainty. I'm going to tell you what it is, what are the source of the uncertainty, and how can we estimate the level of uncertainty on rates for fundamental atomic processes. This talk is probably not going to be a kind of tutorial, as so far we have not yet established a kind of standard consensus on this problem. Although the spectrum error is not a new idea, people know this long time ago from the beginning, but it gets sufficient attention only quite recently, thanks to the Hitomi spectrum of the Perseus cluster. The Hitomi spectrum is a kind of combination of sufficiently good instrument and sufficiently simple object, which is just idea to test detail of the plasma model. Before Hitomi, when dealing with discrepancies in the spectrum fit, people could accuse the source modeling or instrument effect instead of plasma code error. Such excuses are not working very well with the Perseus spectrum. Recently, the spectrum uncertainty have received unprecedented attention from the Christian community. Members of the community are now asking for not only accurate atomic model, but also some estimate of the systematic uncertainty associated with the model. Okay. Where they come from? All the atomic data from theoretical calculation or lab measurement come with an error. By putting this data into atomic code, the error propagates into a spectrum diagnostic like line energy, edge energy, line shape, ionization concentration, emissivity, etc. And worse than the data being uncertain, sometimes we found our plasma code are missing some atomic levels or transitions. The incompleteness will also contribute to the spectrum error. In addition, there also could be numerical or mathematical errors, such as uncertainty caused by linear or logarithm interpolation between the temperature grid sets in the pre-calculation of your model spectrum. Why do we care? First, I'm afraid that we still know little about this error. Not all the theoretical or experiment paper or database provide uncertainty of the atomic constant. Empirically, people like to put something like 20 to 30% to some of the Liyi flux. Assuming those estimates are valid, we already find the spectrum error is kind of comparable or even higher than the uncertainty from the instrument calibration of your X-ray data. Therefore, this uncertainty will affect all science, but in particular for things like abundance or column density measurement. The most solid estimate of atomic uncertainty is basically achieved in the lab measurement. However, in lab, we could test only a small portion of the entire database. And due to all kinds of difficulties for the moment, it is a kind of common practice to assume no model error in the spectral analysis, which is obviously not true. And the current approach is perhaps not going to work for the future spectroscopy with Christian or Athena. So I give a simple example. For instance, the uncertainty of emission line in a collisional plasma is affected by, you can see here, more than 10 processes. The line flux is basically proportional to the ion concentration times the level occupation of the upper state and the relative transition from the upper to lower state. For the ion concentration in history, the overall ionization and the recombination rate, which determines the concentration, has been calculated several times, and now we're using mostly the bryons and the Wood-Empilator rates. And the level occupation is affected by a large matrix of transition rate, in which for the collisional plasma, the collision strength is important in many places, but it is not always the case. And then we also have issues with the Einstein A value calculation and the radiative branching ratios. So this just basically gives you an idea how complex the system is. And even worse, I could tell you that we are now using a lot of theoretical data, and those data in the plasma code are generally taken from two very different theoretical systems, the distorted wave calculation and more recently the R matrix one. The theoretician would expect some disconnection between the two systems. So it is therefore hard to assume a uniform uncertainty for each of the processes. Comparing to the flux error, the uncertainty of the light wavelengths or the edge energy are much better defined. So we can refer to the lab measurement accuracy. For the K shell, the light center are measured to 10 to minus 6 for the hydrogen-like and 10 to minus 5 for the helium-like in the lab. We have several measurements in the L shell at a level of 10 to minus 4. And for the inner shell lines, we are missing, of course, a lot of them. But for the existing one, the uncertainty around 10 to minus 4. So it is quite clear, and we are fully aware the importance of wavelengths, in particular for high resolution spectroscopy. The Hitomi data of the Persis cluster is perhaps so far the only case where the iron helium beta line and the nickel line are resolved at their K shell in a cluster spectrum. But if you fit the Persis spectrum with specs version 2, also called nickel code, the nickel abundance will be wrong because the nickel line wavelengths in the specs version 2 are off. So the correct nickel wavelengths in specs version 3 and the improvement in the instrument spectrum resolution are both essential to the final accurate nickel versus iron abundance ratio measurement made with Hitomi. Error in the ion concentration. It is always a kind of hidden problem. Users are not fully aware of that, and the detailed balance are relatively hard to test with standard lab astral measurement. In Hitomi atomic paper, we have compared the ion concentration used in specs and AtomDB for 4 kV plasma, and similar work has been done for more temperature, more element, including argon, shown here. It becomes clear that if you look at the most populated ion, the peak one, it is in general well consistent among different calculations, while the problem are mainly in the off-peak populations, those lowly ionized populated ions are much less certain than the peak one. Of course, for collisional plasma, the electron impact excitation are no doubt one of the dominant light emission process. As again, we have put in the Hitomi atomic paper, the theoretical cross-section of hydrogen-like silicon 1s2p transition varying about 30% at 4 keV among different code, directly leading to about 30% error in the silicon abundance. The hydrogen-like iron looks much better in the comparison, while the helium-like iron, in particular this 1s, 2s excitation, is again quite uncertain. But later we find a problem with this plot because the red and the green data, they have issues in the calculation. The problems is on this radiative damping correction, while the blue and the black one are better from the theoretical viewpoint. So the remaining difference is about 10%, which is much more acceptable than before. So in general, the collision excitations rate should be considered as a kind of difficult atomic constant, not only because the associated uncertainty can change strongly from case to case, but also the underlying calculation could be tricky, even for experts. It is not always straightforward to obtain the line emissivity from excitation or recombination rate, as there are also cascade contribution, which change strongly for different lines. In the Hitomi atomic paper, we studied formation process of helium-like iron, the W and the Z line. As shown in this plot, the W line is obviously sensitive to the collision strength of 1s2p transition, while for the Z line, the cascade from high levels become much more important than the direct excitation. So estimating uncertainty of the Z-line will cost a systematic recalculation of the entire level population. The same occurs to the L-shell line. For example, the neon-like iron M2 and the 3G line at 70 Angstrom, they cascade from higher levels, dominant, so the line flux are actually more sensitive to the excitation rate to the higher levels. So far, I have shown many aspects of the problem. Now let's think about the solution. First, I would like to emphasize again that so far there's no obviously correct way to estimate spectral model error. Our understanding to the problem is still evolving. So we have many methods. Perhaps we need to test method A, B, and C and see which is the best. For method A, which is the easiest one, is simply to try different spectrum code in the analysis. The AtomDB, specs, Chianti, Cloudy, etc. Like we did in the Hitomi atomic paper, we have fit the PERSIST spectrum with several code and even several versions of the code, and a comparison of the fit might give some kind of estimate of the systematic uncertainty on science parameters. However, one should also be aware that in many cases, the code agree better than their true uncertainties. So sometimes this kind of comparison might underestimate an error. But even so, I would still strongly recommend users to indeed test your analysis with multiple spectrum code, which is so far the most practical and easy way to improve the reliability of your science results. Method B, study the sensitivity of spectrum diagnostic to underlying atomic data. Here I plot another example from the Hitomi atomic paper in which we simulate atomic data for the helium-like iron based on empirical atomic error and calculate the scatter of the resulting line flux, W, Y, X, Z, or the line ratio based on the randomized atomic constant. However, one problem with this method is that the empirical atomic error are known only for a small set of data. And even worse, these kind of error for different transitions might be correlated in their nature. So I know AtomDB team is working on such correlated uncertainty, and they have some promising tool to correct the atomic error to specific kind of estimate the specific spectrum diagnostic. For sure, this will be very useful diagnostics. And finally, we have method C. It's a different approach. It is based on real observations. Here, it is a very simple idea. Assuming the instrument calibration and astrophysical modeling, they are all perfect. Then the spectral model error becomes the only uncertainty left in the modeling of your astrophysical spectrum. And therefore, it should be equal to the error needed to obtain ideal fit of the spectrum. So we have made several exercises on this idea to estimate line flux error. So the test is to first build a kind of sophisticated model, including all kinds of known astrophysical and instrument effects, and then allow the model line emissivity free to fit, the change between the original line flux, and then the optimized line flux should be regarded as a kind of approximation to the spectral model error. So our first exercise is done with a standard source, again, with the Capella HTG spectrum. As we did in a recent paper, we have modeled the spectrum with a kind of multi-temperature modeling, and then we did a lot of correction using astrophysical and instrument issues. And below, then you can see we have the results. The blue one are the original model using multi-temperature and the corrections. And the red one is the optimized line flux using the free fit. And then on the bottom, you can also see their relatively ratio, the relative change of this method. They show here. You can see both positive and negative differences. Okay, then we can collect all these line ratios, and we can put them into a plot. So in this plot, we show each point in this plot is actually one line. So we show the uncertainty we estimate with our method against the line emissivities, associated line emissivities. And we can see for the strong lines from the Capella spectrum, the uncertainty is around 10%. And when you go to the weak line, the uncertainty seems to increase by a factor of 10 or even higher. This obviously shows that the weak lines are much less certain than the strong lines. And also we find, looks like there's a kind of power law dependence between the uncertainty and their emissivity. And this is for the Capella, but what if for other sources? So here we have done the second exercise for another HDD spectrum of HR1099. Capella is a 0.5 keV source, and HR1099 has a temperature distribution peak on 1.5 keV. And these lines are different now, but it looks like this line emissivity and uncertainty relation is basically on the same range. And we have done the third one is for the Percy spectrum using Hitomi. It is 4 keV now, so the lines are completely different, but we can see it's still falling to the same range. So it looks like all these observations, they converge to a kind of similar analytic form, which can be simply described in this power law shape. So, and then we need to ask questions about how the observed uncertainty emissivity relation is sensitive to all kind of effect. For instance, on the ions. As you can see in the plot, the spectrum line from different ions for these two objects, they tend to follow the same analytic form as I showed before, indicate that the relation we found is basically independent on the ions. And in a similar way, we prove that it is further independent on the wavelength of the line, the formation process, the object or temperature, and also the instrument. This study is basically based on a different system. The effect of instrument calibration and astronomical effect is expected to be minor. So we would like to check this relation with theoretical approach, which should include the correlation stuff, and they should be able to reproduce the observations. And if there indeed exists such kind of universal relation between the spectrum error and the line intensity, it will be quite interesting and rather easy to implement in spectrum code. And it can be, well, easily used for the user to give quick estimate of the spectrum line error. So summarize, I think everyone agree now that we need accurate atomic data to match with the capacity of Christian and Athena. And at the same time, we will not be satisfied with zero spectrum error assumption. However, for the moment, there's no straightforward way to answer how the spectrum code uncertainty will be estimated. In the lab, the atomic data error is associated with instrument error, the polarization correction error, and etc. In theory, the uncertainty can be estimated using, say, the correlation study with fundamental calculations. And we could also test the sensitivity of spectrum diagnostic based on the perturbed rates. Any observation, I just showed that the spectrum line uncertainty seems to be in a power law function with a line emissivity. We will still need to see how this approach converge. The error might be also model dependent. For example, the photoionized plasma model might have the different error as a collisional plasma. And finally, the spectrum error should not be a constant over time, as nowadays all theoretical calculation lab measurements are dynamically improving. the atomic uncertainty is expected to improve. So we will get smaller spectral uncertainty perhaps in the future. Okay, so that's all I have, and thank you.
Thank you. Your timing was within about eight seconds. Very good. So we have a couple of questions from Nicholas Gorgon. Does varying the emissivity ignore possible line energy shifts, such as was the case for the nickel in the Hitomi-Perseus spectrum?
We have applied some correction in the line center to this method also. So the line center basically also is able to change a little to correct such effect.
Okay. It's from Travis Court. Have you found a magic number of different spectral databases to use? Obviously, more is better, but would 2 or 3 demonstrate a convergence compared to all the ones that are available now?
So I don't think we have many code. Usually we have 2 or 3 of them. So we are limited by the availability of the code. I think 2 or 3 is enough for the moment. As I said, this is not the ultimate solution because, you know, comparing code sometimes will underestimate your errors. Of course, that will also, if there's some apparent error in one code, it will give you a very easy way to find it out. So that's why I still recommend user to use this. Maybe ultimately not eventually for the uncertainty, but just to check your results.
Okay, and then we have a question about from Chris Doan. Is there any idea how to do this for photoionized plasmas?
If we can find some photonized plasma spectrum with the same quality as this one, maybe not just 10, or it can be slightly worse, but if we can do the same thing using standard one, if we know all the science, all the astrophysics, then it's possible that we can do the same exercise and we can estimate the uncertainty with emissivity relation. Yeah.
Okay, from Victoria Grinberg, do you have an opinion on how best to incorporate the atomic data uncertainties into the spectral modeling packages? And what do you think about MCMC over models with slightly different atomic data?
So you're talking about the fit, or what? Actually, I'm not 100% sure why this refers to MCMC.
How to put the uncertainties into the modeling package.
Sorry, yes, I heard. So in the end, the best way is we can find an error for each line. If we can find that, it will be very simple, straightforward implementation. But if not, we got still several ways. One stupid way is to have one error for each atomic constant, and we need to run a set of simulation inside spectrum code to give you an uncertainty in the end. But that's perhaps too much time consuming. And there might be a smart way to do that with some mathematic tools. Anyway, the easiest way, as I said, is always if we can find an error for each line, then it's best. We can give you directly the error of your spectrum. Yeah.
Okay, and let's see. There's a question from Hiroya Yamaguchi. Does SPECS have a function to vary emissivities, or did you do some special things?
For the moment, I don't think it has a standard command to do that. Usually we need to do some offline program, but I guess we could try to think about this in the future and try to make one in a standard program. Thanks.
Okay, and I think the last question from Pingju, how do you interpret the observation error and its relationship to the emissivity? Is it still related to theoretical uncertainty?
I think so. That's our assumption, basically, as we assume the other errors being lifted out by our very good corrections. So the atomic error is perhaps the dominant factor here that we can get from this free line flux fit.